Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Con? Yes. Okay. Okay. So you know me. My name is Sriram, and this is a crash course on model checking. So the question you're going to talk about today is the model checking question. Is that, does a model satisfy a property? And hopefully I'll try to define each term before I use them. So I'll try to say what M is and what phi is and what satisfy really means. To restrict my scope of investigation, the kind of properties that I'd really be interested in is temporal properties, which means things like if you open a file, you eventually close it. If I do a request, then I eventually get a response back. Or at all times, two processes don't get into the critical section at the same time. Things like that. So what I really mean is temporal logic model checking. So I'll take each one of these questions. What is M? What is phi? What is satisfy? So what is M? To me, M is just a state machine. So I'm going to assume a finite set of states. And my state machine is going to have states and arcs. And in addition, it's going to have colors on the states. By that, what I mean is I have a bunch of atomic propositions that my specifications can refer to. They are of the flavor x equals phi or b equals true or something like that. Where x, b are variables in my system. And then an observation is a valuation to all these propositions. So if there's k propositions, then there's going to be 2 to the k colors. Right? And the reason the colors are not really useful if you're going to write a paper or present something, but in a talk it's very useful, because if I label S2 and S2 to the same color, what it really means is that for an external observer, those two states look identical. So my model is really a label state machine. I'm going to have a finite set of states, and some of them I'm going to call initial states. I'm just going to have a transition relation, which is a bunch of arcs. I'm going to have a set of atomic propositions, and then I'm going to have a label that maps each state to a color, which is a set of propositions that are true. Yeah.
So I is W minus the set of initial states?
Oh, no. This is just a description. So this is something, and after the hyphen, this is a hyphen.
You pointed to I, and you said I are the initial states.
I is a subset of W.
And I look at a minus sign. Oh, that's a dash.
Ah, that's a dash. Yeah. That's a comment. So I should have used, that's a comment character. Okay. Right. So that's M. And what is phi? So I already said that I'm going to talk about temporal logics. But there's no one temporal logic. I mean, there's different kinds of them. And in fact, there's a cottage industry of temporal logics out there. There are people who make a living out of inventing them and studying properties out of them. And so we're going to look at a few most common ones. So for each of them, I'm going to talk about the syntax, which is like what formulas are syntactically correct in that logic. And then I'm going to talk about the semantics. So for instance, the simplest temporal logic is the invariant logic, in which you have only propositional formulae, which is that you have atomic propositions. These are all the formulae that can be coded as invariants. So I can have negation, I have conjunction, I have disjunction. Maybe I don't even need all of that. I could probably get it using that. And then the satisfaction really means that M satisfies phi if all the reachable states of M satisfy phi. By reachable, I mean if I start at the initial state, whatever I could reach should satisfy phi. And if this is the logic, then what is the model checking procedure? It's an obvious one. I could just start at the initial states and explore the states of M using breadth first search or depth first search. And at any state, if I violate my invariant, then I could print an error trace, which is actually one of the nice things that model checkers do.
Can you keep that up on slide?
Oh, sure.
So if the atomic propositions can't themselves label states, then in this system, B is basically every node would have to satisfy that same set of atomic propositions.
That's right. What?
That's right.
No. What is your question again?
Well, if you need to say something like x until y, right, you just can't say that.
Yeah, you can't say that yet. You can't say that at all. Right. You can probably say that by adding more state to your model.
But
right.
Normally the way that, I'm just worried about the fact that C is global, but you only really care for certain subsets of the whole in certain states.
Yeah.
The way you do that is you can join them with I'm in this funny state here.
That's right. So invariants are not very expressive, but they're extremely useful because you can always add. Suppose you want to say that A is true until B becomes eventually true, right? What you could do is when A becomes true, you can just turn on a red light in your model. So you can add state to your model and then make invariance very powerful, right?
So you can add state to the state machine.
The state machine,
right?
And then make invariance very powerful.
You reify the stuff as it.
That's right. Yeah. So, but these are the simplest temporal logic that you could write, which is invariance. A more complicated one is CTL, but it's not all that complicated. It's computation tree logic. It's a branching time logic. So there, in addition to these, which are just Boolean, you have three temporal operators. So this is exist next. It's pronounced exist next. This is exist until. It's a binary operator because it has two operands. This is exist globally. So you should just think about this as a single operator. There's two operands, but I just write it like this, right? And what is the semantics here?
Hold on, I got the question. No, okay. I often see the term branching time logic. I know what the logic part means. What does it mean to call something branching time logic? Okay, so there's things called branching time logic and there's things called linear time logics. The reason why these things are called branching time logics is that the semantics, one way to view these semantics is to view them over trees of evolutions of how the system can evolve, right? Suppose I'm in one place. In the next state, I can have three possibilities maybe. And after that, I can have, from each one of them, I have a bunch of possibilities. So I could just sit here and look at my future as a tree. And then the logic is interpreted over that tree. That's what branching time logics are. The other way to view on a system is to think about linear evolutions of the system. And think about a system as a set of linear evolutions. And then have logics over those sets of linear evolutions. And those are linear time logics. So which of these, there exists X and B until that and globally, which of those makes it a branching time logic?
What makes it a branching time logic is the fact that you have in addition to the temporal operators, you have a quantifier in front of that as well. So I'll show you linear time logic, which would not have any of these things. That's what makes it. So what makes a logic branching is this exists here. Right? Okay. So when I define satisfaction, then it'll become a little more clear. Right? So what does satisfy mean? So these are easy to say. Right? So what I'm going to say is, the one thing I have to say is CTL is a state logic. In addition to a branching time logic, it's a state logic, which means that each formulae of the logic is either true or false in every state. Right? So I could talk about a state satisfying a formula or not satisfying a formula. And by semantics, I'm going to inductively define what it means for a state to satisfy a formula. Right? Atomic propositions, conjunctions, disjunctions are very easy to define. Right? Atomic propositions, if a formula just satisfies it, if it's true in that state. Conjunctions and disjunctions are obvious. Negations are obvious too.
I'm sorry.
Oh, sure.
I'm really sorry. People, slow it down, people can yell at me. On that last slide, where did this cap gamma come from?
Oh, okay. So that's good. Actually, I'm glad you're asking these questions because my notation, so this gamma is what maps each state to the colors, right? Okay. So yeah, if you have such questions, ask me. Yeah, that's good. Okay. So the semantics is really in these three. So a state satisfies exists next phi. So S satisfies exists next phi if there exists some next state which satisfies phi. That's the semantics for that, right? A state satisfies, so then this state satisfies exists next phi. Then a state satisfies exists phi next psi if there is a path from the state. And we're starting at S, there is a path here, such that phi is true everywhere, and then eventually psi becomes true. Right? And then exists globally, phi is true if there exists an infinite path in which phi is true everywhere. So that's the semantics.
What is the quantity of like what is B just the next thing and it's
Yeah, that's fine as well. So I see that PowerPoint has capitalized my V. I didn't want it, but yeah.
So if you have the first property that is exists next phi, then that means that you satisfy the property that exists anything, whatever that you think is phi.
No. So you could
So this could be true, and still psi until phi could be false. For that to be true, psi has to be true here as well.
I see. S is included.
Yeah. Okay. So these
So
are
in English, what does the second one say then? Until you get to a state where psi holds.
phi holds. Yeah, so that's what this means. So from now on, phi holds, there exists a path in which phi holds until psi holds. That's what this means in English. This means there exists a path in which globally phi holds. This means there exists a next state where phi holds. Right? Okay. So then what I want to do is I want to come up with a model checking algorithm for CTL. I don't have slides for it because the algorithm is not very complicated. Yeah. So how would you come up with a model checking algorithm for CTL? So I suppose I give you a model and a formula. How do I check whether a model satisfies the formula? I mean, for invariance, the decision procedure is very simple, right? I just have to do reachability. It turns out that all you have to do is then, since CTL is a state logic, you can label each state with the sub-formulae that are true in that state. And if you do it in the right order, then you can come up with a very efficient algorithm to model check CTL. Right? So for that, by what I mean by that is, what do you mean by sub-formulae? Suppose I give you a formula that looks like this. Right? The subformulae of this formula are all these. X is xq, and if I call this formula as phi, is the formula phi itself. These are all the subformulae of this formula. Right? Then what I do is sort of order them in such a way that the subformula of this formula comes before that formula.
Yeah, sorry, I didn't understand that formula.
What's
What is the bracket in there?
Oh, so what I've done is, this is exist blah until blah. So think about this as phi, and this is psi. Right? So that's why this is a CTL formula. Right? And this formula is itself another CTL formula. Right? Which is exist GP. Okay, yeah, feel free to ask these questions. Right? So by subformula, what I mean is, in every formula, I just write the components as well, and then their subformula as well. Right? So for this formula, these are all the subformulae I get. Right? And I could sort of order the formulae in such a way that before a formula shows up in my ordering, all the subformulae of that formula show up in the ordering.
So
right?
If I think of the abstract syntax, this is just bottom up.
This is just bottom up. That's right.
There's no other sort of ordering I have to worry about, is there?
There's no other sort of ordering.
I don't have to worry about left to right of this.
That's okay. I mean, I could just transpose these. There's a bunch of orderings that might be good for me. Yeah.
Okay.
Right. So there's a topological order, and after that, any linearization of it is okay. Right. Then what I could do is I could tell you how I could label each state with a formula, assuming I have labeled states with a formula that happened before that. Right. So labeling atomic propositions and conjunction distinctions is easy. Right. So I'm not going to worry about them. The other ones are also not all that easy, not all that hard. Right. How am I going to label a state with exist next phi? All I'm going to do is I'm going to check states that have the label phi in them, and I'm going to just look back at them. And every state, I'm just going to label ex phi. Right. So that takes care of that. Right. How do I take care of exist phi and psi? Right. Someone wants to guess.
The idea here is that we're trying to label states instead of subforms, so which those subforms are true.
Yes. Right. So how would you do this? Okay. Suggestion to this. Right. Suppose I already labeled phi and psi. Then how do you do it?
You hold phi, and then you see if you can reach 2 phi, and then you hold that psi.
That's pretty good, right? But it's more efficient to do it backwards, because if you do it forward, then you have several steps to do. So what you could do is you could start with the ones that have psi, and then label them with exist phi into psi, right? And then you could go back, and as long as you are satisfying phi, you could continue to label them and keep on doing it, right? Right? Then how do you do this? Exist globally phi.
So what you could do, so the easiest thing is to do is to find the strongly connected components, because then you have to look for cycles and things. So what you do is you just restrict your graph to the nodes that satisfy phi. Right? So you take your model. Okay, take your model and restrict it to the things that satisfy phi. So you have a different model now, just like a sub-model of that one. Right? And then you find the strongly connected components in the model. Right? And then all these strongly connected components have some cycle that satisfy phi. So by definition, all of them are going to satisfy phi. But I'm not done yet, right? I still have to go back from the strongly connected components as long as phi is satisfied. And those satisfy e.g. phi as well. Right?
So it's really any node that can reach through phi a cycle of phi.
That's right. That's all it is. So this algorithm is really famous. So it's called the CES algorithm. And it probably has like 1,000 citations. So you wonder why you did not come up with it. But I'm sure that hindsight is useful. Yeah.
What does CTL stand for?
It stands for computation tree logic. Yeah. So the CES algorithm is by Clark, Emerson, and Sisla. And they actually it's a little more complicated than this, because there's something called fairness, and the the CES algorithm works with that as well. But I'm not going to get into that. Right.
So can you go back? So I can see how you can construct all the problems. You can label all the nodes with these propositions. But I'm still not convinced how you can. The point was, if you do this bottom-up, it's efficient. And I don't see how that is the case yet.
Okay. I'll answer that. Do you want me to answer that first, Vinod? 1 second. So, yeah. So the deal is, if you don't do it backward, then what you could do is, the forward algorithm could do something like this. If phi is true currently, and in the next state exists phi until psi is true, then in my state add phi and exists phi until psi as well. That will be the forward algorithm, right? So each iteration of the algorithm takes time that's proportional to the size of the graph. And the number of iterations you have to do is again proportional to the size of the graph, which becomes sort of n squared.
So that essentially encodes breadth first search, that algorithm you just disclosed, right?
That's actually a nested search. This actually does it in a single search.
Right. Well, it's not search at all, right? Because it's much more like the Lee-Moore router algorithm.
That's right. It's like backward propagation. That's what it is. Yeah.
So the complexity is size of formula times size of...
Yeah, so the complexity is the size of model times the size of the formula. I haven't said what it means for a model to satisfy a formula. Actually, I haven't written it here. What it is actually is, if all the initial states of a model satisfy a formula, then a model satisfies a formula. Right? So that's what we mean when we say a model satisfies the city of formula. You had a question? Or Vinod had another one.
Yeah. So the simple formula is very nice and pretty. Suppose you have conjunction and disjunction.
It's okay. Right? I mean, you could always.
You need to set a set of states then, or
Yeah. So for conjunction and disjunction, you have to do disjunction and conjunction in the usual way, but that doesn't involve any temporal operators in it. If phi and psi are both satisfied, then you say phi and psi.
But then for outer temporal formulas, you have to restrict your search within those. Right?
No, when you're dealing with any formula, right? If you label the subformula, then you don't worry about how the subformula got evaluated.
So you restrict your search at some point?
No, you don't restrict your search at all. The only place where you restrict your search is to do e.g. phi. But you restrict your strongly connected components to the ones that satisfy phi. Tom.
So one can sort of look at this as a deductive process. I'm thinking of sort of like in data law, you have this bottom-up evaluation. Part of the problem with that is here you're going to label certain states with facts you probably don't even care about.
Yes.
So in data log there's this thing called magic sets, which is if you have a query at some node and you want to know the formula, then you sort of push the knowledge about what you know in that formula down into the query, and then when you're doing your bottom-up evaluation, you have this nice property that you only ever derive a useful fact. You never label something that's useless in the end.
So for instance, so to accentuate that, I could have a true OR and a clumsy formula here. And to evaluate that formula, then I have to label everything anyway. So there's actually another cottage industry on how to do this efficiently. And there's like a bunch of papers, lots of them. And the things that you described, there's approaches similar to that using there's also people talk about
like forward which is backward. There's techniques that can do forward CTL more efficiently than the more obvious ones as well. So there's actually there's a wealth of literature on this stuff. Yeah. So I don't know anything concrete that I could just say along the lines that you said. Okay, so I'm going to now describe a linear time logic. So syntactically, it looks a lot simpler than the other one. Actually, before I do that, I need to also say a few more things about branching logics. See, all these quantifiers that I have are existential, right? But you also have universal quantifiers if you apply negations, right? So, for instance, there's a few abbreviations that people usually use. This is usually written as, this means finally P holds, event. There exists a way in which P can finally hold. That's just abbreviation for that. And then, this is nothing but always P holds. It's like an invariant. Right? So that's why invariants are a proper subset of CTL. Not there exists F, not P. Right? And then you could also write for all FP, which is not there exists G, not P. This is always, among all paths, P will eventually hold. That's what this is. Right? So you could write things like that. And you could also write this. This means among all paths, P will hold until Q holds. I'll leave this as a homework exercise. It's a little bit tricky to write this as in terms of the other ones. So in a similar way, right, using that, try writing this. So you sort of understand what it takes to do these things. So what is LTL? In LTL, the reason why it's linear time is that you talk about only executions. So you define LTL semantics on linear execution. So all your models are going to be straight lines. There's going to be states. There's going to be no branching. Since there is going to be no branching, I don't have to worry about there exists something or always something. So the path quantifiers don't exist. And so in some sense, LTL is a much simpler logic, syntactically. But semantically, it's much more complicated than CTL. Right? Which is why I did CTL first. So this means phi is true. This just means phi is true for a while, and then psi holds. That's pretty much all the temporal stuff that is. Actually, I also need the next. I haven't written that. So you also need x phi, which means in the path, phi holds in the second state. That's all that x phi means. So this is the syntax of LTL. And it turns out that it holds once. In the until, the semantics is phi holds for a while, and then psi holds eventually. You can have the always using the negation. Right? You can negate such things and get eventually, always, yeah. So I'm not going to go through the model checking algorithm for LTL. The one thing I'll say that it is p-space hard. So the only known algorithm is linear in the size of the model, and it's exponential in size of the formula. Right? So, but yeah, I'm not going to go through it.
Very common. I mean, you showed this other thing with the tree, which is here. This is just a linear sequence.
No. So one thing I did not say is that a model satisfies an LTL formula if all paths from the initial state satisfy the LTL formula. Right? So I've defined the LTL semantics only for a path yet. Right? Now I have to also say, when does a model satisfy an LTL formula? So I have to say, M satisfies an LTL formula phi if for all paths pi, right, in M, pi satisfies phi.
So you're saying that complexity different attributions is notion of satisfaction, whereas in CTL we have the notion of satisfaction that all initial states satisfy formula.
You could say that, right? But it'll be a loose statement to make. I think the hard thing is that you cannot do divide and conquer in LTL very easily. But you can't sort of label states with their subformulae. Because you can't have, so it's very hard to start labeling states with it. I mean, if you write an arbitrarily complicated LTL formula, there's no way to just divide and conquer it. If there's a way, then it won't be p-space hard. So that's the only reason.
So I'm using some intuition as to why in the ETL logic you say the model satisfied if the initial state satisfied. Whereas in this logic, you say the model satisfies only all paths satisfied.
All paths starting from the initial states.
Right. So why that distinction, and what is the significance of that? And so conceptually, what does it tell me that a model satisfies in CTL? Say a model satisfies some proposition. What's special about the initial state?
Okay, so what it really means is that, so let's say for simplicity, let's say there's only one initial state. I think that will elucidate the point very clearly. So what you say when a model satisfies a CTL formula is that you start with the initial state and sort of unwind the model, and you get a tree. Right? If your model is like this, your model can have like cycles and everything, right? But if you sort of unwind it, maybe you'll replicate states multiple times, and you'll have a huge tree before you. And the CTL semantics is set on the tree, right? That's what the CTL semantics is on. It's on the tree, right? That's why it's a branching logic. The linear logic is you have a lot of paths passing through, and every path must satisfy the formula. Yeah.
So are you saying then that if the initial state satisfies the formula, all the states are going to satisfy the formula?
No, you're not, right? But if the initial state satisfies the formula, then the model satisfies the formula. I'm just giving you a definition.
Right. So I want to understand why that definition is interesting. Why not the definition that the model satisfies the formula of all the states satisfied?
No. Oh, why is it interesting? Yeah. You might want to say, that's because, see, I'll give you a formula, right? Maybe the initial state has some property that P is true, right? And then eventually P becomes true in the initial state, right? But maybe there is some other state here in which P doesn't become true, and that state does not satisfy FP, right? But when you're talking about the system, you're talking about the system satisfying P, because when you state properties of the system, you're talking about properties of the system starting from where the system starts, right? So that's how you define it. But there's nothing deep in that. Okay,
but then there might be other properties where you actually care that the property holds in all the states.
Yeah, but you could state them as well, right? For instance, you could state them as...
state them all in terms of the initial state because it's got this temporal specific.
So you could, if you want all states to satisfy a property, you could just write always globally, then the property phi holds. So you could state that as well. Right? Actually, just note that the distinction between LTL and CTL is quite subtle. Is that when experienced people make lots of mistakes. Yeah.
So is there inclusion either way?
So neither one of them is more expressive than the other. I could write CTL formulae that cannot be written in equivalence don't have an LTL, and vice versa.
Because there's this classic picture I've seen of the two trees, right? The one with A and then B, C, and the one with A, A.
Yeah. So
the one that distinguishes.
So the one that you said is a CTL formula that does not have an equivalent in LTL.
Right.
And you could also have
You can have it the other way.
You can have the other way too. So from expressiveness point of view, they are not compatible. Okay. So just to give you an idea that there are a lot more, this cottage industry is huge, I'm just going to throw one other one. But I'm not going to just go into this in great detail. There's something called the modal mu calculus, where these are sort of similar to what you have seen already. But then you can have these functionals, and you could talk about greatest and least fixed points. And there's a notion of satisfaction, which I'm not even going to get into. But the interesting thing about this is that the complexity of model checking this logic is not even known. The model checking problem is known to be in P. It's also known to be in co-NP. It's known to be in NP. It's also known to be in co-NP. And that's all that is known about this logic. So you could write really simple things, like in a slide for which model checking algorithms could be pretty complicated. Yeah. So the other thing you could do is actually, so designers actually hate these logics because they just, for starters, they are in Greek, and they're hard to understand. So you could also write specifications that also sort of look like your models. Right? So you could write your specifications as state machines as well. So then your model checking problem sort of becomes like the refinement checking problem. Right? So in that, what you do is your specification is also a state machine, and it also has the same set of colors that your implementation has. It has different set of states, but the commonality between these two is in the colors. Right? And then you say that an implementation satisfies a specification if every behavior of an implementation is an allowable behavior of the specification, and you use the less than sign to relate. Okay, so
I did not know what happened.
So every behavior of the implementation to allow.
So I'll state it more precisely. In the next couple of slides, I'll state it more precisely. That's the intuition. I'll state it more
So
precisely.
you think the implementation should not do anything that is outside the specification?
Yeah, the specification disallows. Yeah,
But it doesn't have to do everything in the specification.
it doesn't have to do. The specification could be like non-deterministic. It could allow a lot of behaviors. Right? An example of that would be the specification could be an instruction set architecture. Right? And the implementation could be a pipeline implementation. It could be an instruction set architecture that allows an arbitrary amount of delay between the time an instruction comes and it gets executed. And every pipeline that implements it sort of just makes their own performance decisions to implement that. But the semantics has to be maintained. That's the only thing. Right? So formally what it means is I have these models, and then I have runs, which are just starting from the initial state. I have paths, and then I have traces, which are just, if I just forget the states, I look at the colors. Then what I really mean by refinement is this trace inclusion. Right? So every trace of M should be a trace of S. And this is language containment. So you could do it using automata theory.
I'm just trying to think about what you said.
Mm-hmm.
It's more time. S is the specification? And
Yes.
M is the program.
M is the model.
Or model.
So usually I used to use phi, but now since this is a state machine and this is friendly to designers, I've started using English letters for that. Yeah.
So you need a class out duplicate, duplicate colors. So M could go red, 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 red. Red. And those are one straight.
So M could go red, 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 and then so I'm assuming that the colors are sort of common to both, but the states are not common. I did not understand your question.
Okay, it seems like the traces in M were spread out.
Oh yeah, yes,
You
yes.
have to project it onto S.
So you have to define the notion of colors appropriately. For some notion of colors, it will work out. Yeah. Okay. So that's the only reason why you use colors, is because if you want to compare two things at different levels of abstraction, you have to have some common language to compare them, right? And in a presentation, it makes sense to call them colors. Yeah. Right. Okay. So it's even though this is sort of like a very simple way to specify things, you don't need logic to do that. There's intricate connections between refinement and logics, right? So these two statements are equivalent. If M refines S, that is equivalent to saying that every linear temporal logic property that is true in S is also true in M. You could prove that these two are equivalent statements, right? So even though you don't want logic is like behind the scenes. It's there, right? And then the complexity of this is exponential in S, because complementation. Right? And the next week I talk about some work.
Okay. LPR because we're looking at this fast.
Yes.
And we're checking on.
Yes. So similarly, you can also have a notion of branching refinement, right? That's actually called simulation. I'm not going to talk about it. And then there's a corresponding analog with respect to branching logics. So there's an intricate connection between refinement, depending on what notion you use, and logics. Right? But again, I'm not going to worry about that. So the story so far is that you can have models and you can have all these logics, and you can have model checking procedures for them. And some of them are polynomial, and some of them are exponential. But the real problem for a practitioner is not the fact that all these logics exist and they have model checking procedures. But the fact is that the model itself is something that we cannot comprehend or build or anything, because the models are pretty huge. So for any tool builder, the real problem is that for a theoretician, M sort of exists. But for anybody who builds a tool, M is the real problem. You can't even sort of build M, right? So M is exponential in the description of M. For instance, if you are talking about circuits, then you're going to be given a succinct representation of the model, namely the circuit. And then you have to reason about the state space of the circuit. Similarly, if it's a concurrent program, you're going to be given the program text, and then that's the model. And this model is exponential in that model.
So the size of the model is actually the number of states.
Is the number of states, yeah. Right. So the majority of this talk is going to be in fighting this explosion. So that's why the model checking and the logics actually, I'm just going to give that as an introduction. Right. So in fact, what I'm going to do in how much time I have is talk about ways by which I can contain the explosion in M from its succinct description. I'm going to talk about methods that are more automatic first, and I'm going to talk about BDDs, which are symbolic methods, and then I'm going to talk about a particular method called partial order reduction,
And if I have time, I'll talk about symmetry reduction today, but maybe not today. And then next week, I'm going to talk about divide and conquer, which these approaches are less automatic. And this is a tool that I worked on as part of my thesis. So maybe I'll have some chance to talk about that. And then I'll talk about abstractions.
When you say less automatic, means requiring human
intervention. Yeah. So today, I'm going to talk about the more automatic techniques. Okay. So all of them actually require some tweaking, but it's the degree that is different. Right? And when I'm considering these, I'm going to consider only the simplest logic, which is invariance. Right? So you could write a lot of papers for each of these methods, for each of those logics. But to focus on the explosion, I'm just going to consider the simplest logic, right? Which is invariance. And next time I'll probably talk about abstractions and assume guarantee. And if anyone shows up the last time, I'll talk about applications to software. And how some of these techniques have been used in software. What has been done so far. There's been some work in using it for specifications. And believe it or not, some work that has been used for checking it on actual C code. So there's a reason why I put it in the last class, so that people will show up. Yeah.
Are you familiar with the shaping work, which is a really good, concrete, actual expansion of the Veritas work?
No. You should probably give it to me. Yeah. So I have 2 weeks, so I can digest it and present it as well. Yeah. Okay. So I'm not familiar with it. So today I'm going to talk about the more automatic ones, and the first one is symbolic methods. So what are symbolic methods? This Brian came up with this thing called binary decision diagrams 10-15 years ago, and he didn't come up with it with model checking in mind. I mean, he wanted to just represent Boolean functions efficiently, right? So I'm going to talk about what BDDs are, and then I'll talk about how they are used in model checking. So if I just want to implement a Boolean, represent a Boolean function A XOR B XOR C XOR D, right? I can represent it as a decision tree. So, but for most functions, there is a lot of commonality and redundancy in this decision tree. For instance, in this, right, this and that are sort of isomorphic, and so are this and this. And there's a lot of redundancy. So what you could do is you could do two things. If two nodes are isomorphic, you can sort of merge them. And the second thing you could do is, if I have a node P, if I have a node A, for which both the 0 child and the 1 child point to the same node, then I could just yank that node out and then connect everybody who's connected to A down there, because there's no decision point that is made there. So if I do those two reductions repeatedly until I can't do any more reductions, then I get a BDD. For instance, if I start with this and I do this, you will get this. And the nice thing about this is, once you give an order, they are canonical. So there's only one such DAG that you can come up with once you fix the order A, B, C, and D. Right? So it doesn't matter the order in which you do those two reductions. You'll always come up with it. And they are, for a lot of common functions, they are very compact. And this example sort of gives you an intuition as to why they are compact. Suppose, let me just define something called a cofactor. So a cofactor is something which you take a function and you hardwire some values into it. Like for instance, if I take the cofactors of this function with respect to A and B, right, there's 4 cofactors. I can have F00, F11, F01, and F10. Right, which means that if I choose the values for A and B, I can choose them in 4 ways. So I get 4 different functions. But usually there are not that many functions, right? So here, right, these 2 functions are sort of the same, and these 2 functions are the same, right? So here, right, if I choose 00 or 11, or 01 or 10, the information I have already chosen doesn't actually distinguish me in several ways. For several practical functions, that's the case. So even though there are, if I'm depth k, I have 2 to the k different cofactors. There's only a small number of distinct cofactors. And what BDDs do is that at each level, they represent only the distinct cofactors of a function, right? And that's another reason why they are canonical, because cofactors are independent of the implementation of the function. They say something about the semantics of a function, right?
But this is useful only if you don't have to first start with that representation and produce the BDD.
Yeah. So you don't have to. So that's right. So what you do actually is, what you can do is that if you have a circuit, right, from the circuit you can actually come up with a BDD.
Yeah.
from the structure of the circuit itself. I'm going to show you how to do that. Right? So, yeah, you're right. So, I mean, if you build a truth table and then make this, it doesn't make sense. Right? So there are techniques to just come up with this automatically. So the one thing I'm going to say is the variable order affects the size of the BDD. So you can write functions for which you can just change the variable order. And for one variable order, you'll have an exponential BDD. And for another variable order, you'll have a small BDD. Right? So when you say BDDs are automatic, they're automatic if you give a good order. Right? And then finding a good order is still NP complete. And so it's the really good users of BDDs, they tweak the variable order themselves. So, but they're canonical for a given order. And the question that Manu was asking was, if I have a circuit, right, I can start from the leaves and I can sort of build the BDD for the circuit from the leaves all the way to the root. So for instance, if I have F and G that are inputs to a circuit, and if I have the BDDs for F and G, I can build the BDD for F and G, F by just adding the BDDs. And those Boolean operations are very efficient on BDDs. Right? And so that's why actually the first application for BDDs was actually combinational equivalence. Right? In the hardware companies have gate level models of circuits, and then they have switch level models. Right? And they are sort of there's no state encoding that's changing between those. So what people do is that they extract. So these are just two different ways to implement the same function. So to check whether they don't have any bugs in them, what they do is they build the BDDs for both of them. And since they're canonical, the circuits look different, but the BDDs have to look the same. Right? And since they're canonical, tautology is very equivalent to check. Right? Because there's only one tautology, which is this. Right? So any circuit that is the tautology will look like this if you build a BDD for it.
So and is very efficient. Which operation is the one that's like?
Yeah, that's the one you predicted me. So if you want to do combinational equivalence, actually that's why BDD is just screen. But if you want to do model checking, you need another operation that bites you pretty bad, and that's quantification. So what is quantification? So if I have a function f, the existential quantification of a particular variable v is defined as that. So the definition is you hardwire v to 0, and then you get another function that's independent of v. Right? Then you hardwire v to 1, you get another function, and then you just OR the two functions. That's still again independent of v. So and you could quantify multiple variables, exist BC, and it turns out that the order in which you quantify them is not important. You could prove that. You could prove that exist BC is the same as exist CP. Right? For instance, so one way to think about quantification is if you write it as a Boolean expression, and if you want to quantify B and C, just erase them from the board, and you will get the quantification. Right? So the existential quantification of B and C with respect to this function is one in which you just erase the B and C, and you'll get that. Right? But something that's so simply on the board is worst case exponential for BDDs. Right? So if you quantify n variables, right, it can just explode. But it's heuristically efficient. You could do it for a lot of things. It works well. So far I just talked about BDDs. Now I'm going to go back to model checking, and in particular I'm going to go back to only invariant checking. Right? That's what I'm going to talk about. So to do that, I need to represent two things as BDDs. The first thing I have to do is I have to start representing sets as BDDs. Right? So let me just assume that my model has Boolean variables. If it has non-Boolean variables, I can encode it as Boolean variables. And so any set of states I want to represent is going to be a subset of 0, 1 to the n. Right? So the idea is that I can represent any such set by its characteristic function, which is a Boolean function. Right? So for instance, if I have this set of 4 states over the domain over the variables x, y, z, I can represent it by its characteristic functions x plus y plus z. And the characteristic function I could represent it as a BDD. Right? So that's the basic idea. So the idea is represent characteristic functions as BDDs. Now I could do set operations as BDD operations. I have no idea what these boxes are doing here. But they were not there in mine. Okay. So if I want to do union of P and Q, I could get the characteristic function of the union by just ORing the BDDs, and similarly intersection and negation. Right? So I can manipulate sets with BDDs. That's not a problem. The other thing about oh, so this I haven't written this well.
Yeah.
Here is the universal set.
That's the universal set.
Yeah. So, I'm sorry.
So I could also represent transition relations as BDDs, because transition relations are also sets. Right? So I could think about each arc in my state machine as a pair. Right? The set of all arcs is a set of all pairs of states. Right? Now this is also a set. I could represent that using BDDs. But then it goes to the same problem, that I can't draw the state machine and then represent the arcs. I mean, I should come up with this R from the succinct representation. And you could do that for circuits pretty easily. For instance, suppose this is your circuit. Right? So this is much more succinct than the state machine. Right? And you could build R for it directly. All you have to say is that the next value of V0 prime is the negation of V0. Right? And the next value of V1, which is V1 prime, is the exclusive OR of the previous values of V1 and V0. And every transition that you do has to exactly satisfy this. Right? So now you can do two things. You can represent sets as BDDs. You can represent transition relations as BDDs. And once you do both of them, you can use the existential quantification to do the search symbolically. That's why the existential quantification comes in. So I'll show that in the next slide. So, this is terrible. I realized I had chosen a really bad color. How can I do something here? I can just use the blackboard. That's right. So what I've written there is, suppose I have P, which is a set, right? And I want to find the set of all states that P can reach in one step. That's going to be the basic operation that I need in doing this kind of search. The way I could do it is the image of P, which is R. Image of P is the set of all V, such that there exists the set of all V prime, such that there exists some V in P, such that R of VV prime. That's the image of P, right? And I could write that as exists V, the characteristic function of V, and the characteristic function of R, VV prime. You can imagine that to encode this, you need the existential quantification. Right? And so I haven't written that well. And you could also go backward using the same technique. But the deal is, once you have this image operation, then you could actually start from the set of initial states and then keep exploring, like in a breadth first search, without actually representing those states, but representing all those sets of states as binary decision diagrams. Right? So if you want to check whether an invariant V is violated, what you could do is you could start with the negation of the invariant, and that's also again a BDD, right? And you could have the invariant sitting here somewhere, negation of the invariant, and you could just keep expanding. And once you hit the invariant, there are ways by which you can fish out an error trace out of the BDD. So you start with this, and then you just compute the image, and then you union that, and then you compute the image and the union that, and that's what you do. Right? So far so good. Okay. So BDDs are a big breakthrough in hardware. The guy who wrote the BDD-based model checker.
Just want to clarify. But you could construct situations where the BDD is actually no smaller than the...
Yeah, you could, right? Otherwise, you prove P space equals P. Yeah. So I give some intuition for what kinds of things works well with BDDs. So the thing is, when Macmillan did this in like 92, his thesis won the ACM thesis award, and since then actually it has become quite famous. I mean, every hardware company has a BDD-based model checker, and large formal verification teams that are based on them. Right? And actually, you can't believe that people are writing all these formulae, like in an industrial setting, and just there's engineers who don't have PhDs who are pushing model checkers to them. It's quite a sight if you go there. Yeah. So the one thing that BDDs do is that they compactly represent transition relations. You can prove that the transition relations for circuits, for most of them, are actually compact. Because what tends to happen is that if a circuit has bounded communication complexity, you can use the structure of the circuit to come up with a variable ordering, right? And you can sort of prove that the BDDs for the transition relations are compact. But what tends to be really hard is that the images and reachable sets, there is basically no mathematics to help you. And they tend to blow up every once in a while. And they tend to blow up so much that there's PhD thesis written on how to compute images without them blowing up. Yeah?
I think that's the one that's beginning to blow up. So at the tab on Tuesday, you had Richard Newton here. big hardware guy.
Yeah.
The issue of verification of hardware came up. And he said that all these places that are hiring all these hundreds of people to hack the formal method aren't getting the return on their investment right now. He said that it really hasn't been that successful at all. Is that because of the immaturity of it, or?
So I can talk a little bit about that. So what actually happens is, so I can give a short answer to that question and a long answer later. Actually, so what happens is that in BDDs for units, right? So maybe the answer to that is the next slide. So people have just done so much hacks on this, and the bottom line is that if you have over 100 variables in your system, then BDDs tend to work with someone who doesn't have a PhD, right? So if you have 500 variables, then you need someone who has done a thesis in image computation to actually drive them, to sort of do. And there's been so many variations of these, from like ADDs to ZDDs, where people just build a different kind of BDD for arithmetic circuits, one for multipliers, one for floating point units, and you name it. There's something else for there. So what happens is that for the particular hardware circuit you verify, you need a bunch of tricks that are native to that domain to drive the BDDs to go well. And if you can do that, then the BDDs verify units very well, right? They verify control logic really well. So what BDDs can do is that if you take like the description of the power PC and then ask, will my bus deadlock, then BDDs are definitely going to blow. So what you need to make BDDs really scale is that you need some user intervention on top of BDDs. For instance, for my thesis, I was doing compositional verification, which is actually dividing a proof into parts. And dividing requires a lot of user intelligence. And if you have something like that, then you can verify much larger circuits. So in our group, we verified a really large signal processor. But it took us like 2.5 months to verify it, even after building the tool. So the answer to your question is, I think units, people are able to verify. If you take a particular unit, and as long as it has about 100 variables, people are able to verify that. And that's still enormously useful, because there's lots of components with high bug potentiality in them, which are pretty small. And for them, BDDs work very well. But I think what the companies are finding out is that you cannot easily make global statements about your chip. And to get from the unit leap to the something about the system level is something that they are not able to do. And I think the people who sold model checking to them first, like sold that we'll be able to verify entire chips. And then the management is getting sort of dissatisfied with these people, because now they can't prove that the Pentium is right. They can prove only the floating point unit of Pentium is right. And then that's sort of the situation. Yeah. Mm-hmm. So I'm now going to talk about another method, which is it's partial.
So the previous one you made, does that suggest that that bad use of BDD you want to do it on software, because you are going to get lots of variables very fast?
So actually, I personally think that BDDs are not the right way to go for software, because I think BDDs are just like a bit level. And even if you take a small program and start encoding your integer variables or some finite domain, so you just run out of things pretty quickly. So BDDs really work for hardware because the circuit flow sort of gives a natural ordering to the variables. And you can have prove some results that at least some of the BDDs are small. And that's the reason why they succeeded there. I think even for small software programs, BDDs are going to blow. So this is actually not parallel, but partial. And partial order methods, this is actually a different domain. So what actually happened in model checking is that it's a piece-based odd problem, right? But then each domain, people sort of came up with tricks that solve their particular problem. And then when 2 or 3 designs of the same kind have the same kind of tricks, then they sort of unify into one kind of technique. So I'm presenting the most general ones. And you could always find enormous case studies where I have this particular bus controller for this particular processor, and I had to use this representation to model check it. So partial order methods are useful for protocols, actually, where your basic model is actually an asynchronous composition of processes. And here the idea is that you don't do anything symbolic. You still explore states one after the other, but you don't explore all the states. You explore only a portion of the state space. But still, you can make statements about the entire state space. Or you can prove properties about the entire state space. But how are you going to do that? You're going to use the structure of your program to do that. Right? So the process object model is what partial order people usually use. And there you have a bunch of processes and a bunch of objects. And each process, it runs a program. It has a program counter. And objects are shared between the processes. Right? Think about objects as just either variables or shared memory or queues or whatever. Right? So this could be an example of a process object system. So you have two processes and you have two shared objects, X and Y. But they're not really shared because only each one is using its own. Both of them are not being used by both of them. So the first process just checks whether X is less than 10 and then it increments it. And similarly, the other one. So what I want to say is that situations like this can be always modeled in terms of guarded commands. Right? Where what you have is that you have a bunch of variables. And you have a bunch of guarded commands. Each of them have a guard. And then some arbitrary code that changes something. Right? And so this is how I have encoded the previous problem into this. Right? So when I do discussions, I'm going to just use the guarded command model to describe these things. So the semantics is that you have a bunch of variables, and then at each step, one guard. So this is the initial step, and then one guard is chosen, which is enabled, and then it is executed. And then another guard is chosen, maybe the same one, and then executed. The global system is still a label state machine. Right? You could still think about the system as a state transition graph, but it will be much bigger. And the process object model is a succinct description, just as circuits are a succinct description of state spaces. So it's convenient to talk about actions when you talk about partial order reductions. So what are actions? Actions are just labels given to guarded commands. So the one thing is that the non-determinism in the model arises because any of the enabled actions could be scheduled at any point in time. Right? Actually, I started at 5 minutes after the hour. So can I take 5 minutes after the hour? Or are people completely bored? And then I can just stop. So can I have a vote? Yeah, okay. So the non-determinism of the model arises because at any point, any of the enabled actions could be scheduled next. But once you decide which action to schedule, the next state is deterministic, right? So because on the right-hand side, there is no non-determinism of actions. You could also label state machine transitions with action names. And that's quite useful. So for the previous small example that I showed you, this is how the state space is going to look like. I'm going to start with 0, 0, and the alphas are going to increment the x's, and the betas are going to increment the y's. Two actions are independent if this is actually a central notion in partial order reduction. If two conditions are satisfied, neither one enables or disables the other, and if both are enabled, then they commute. So if I cannot have alpha enabled in a state, and then beta not enabled, and then if I have to execute alpha, the execution of alpha cannot make beta enabled, and vice versa. And if beta is enabled, execution of alpha cannot disable beta. And if both of them are enabled, then executing them in either order doesn't matter. I always get to the same state. So that's what's meant by independence of actions. So since I wrote this example to illustrate that, so alpha and beta are independent here, right? Because you have the diamonds everywhere.
So the thing here is that the particular order may have to be irrelevant.
Is irrelevant. So that's actually basically the key. That's what's going to help you do the state reduction. But you could have dependence between actions as well. I mean, I could start and explode a bomb when x is 3 and y is 3. Right? And then what happens is that at 3, 3, then I could execute gamma and then explode the bomb. But then gamma now becomes dependent on both alpha and beta. Right? So you could have, the typical situation is you're going to have some actions that are dependent on each other and some actions that are independent of each other. So the key idea in partial order methods is that if you have a set of mutually independent actions, this is a set of mutually independent actions, then the order in which you execute them in a particular state is not usually relevant. And you need to explore only one. But there are some caveats. And before I get to the caveats, let me just formally define what partial order reduction is. So two action sequences, A and B, are partial order equivalent if you could get from one to the other by swapping adjacent independent actions, right, any number of times. So that's an equivalence relation on action sequences. And the idea is to explore only one representative in each equivalence class. Right? So the take one on a partial order reduction, I mean, suppose when you had come up with a partial order algorithm, this is probably what you would first come up with, and it's wrong. I'll show you why. So the idea is, Suppose I'm in state S, right? And there's a bunch of transitions that are actions that are okay to execute here. And what I do is that I execute only a subset of them, say delta, and I don't execute the remaining ones. These I don't execute. And I can do that as long as every action here is independent of every action here. The reason for that is, since it's independent, I can always execute these later. It doesn't matter. I mean, I have not lost anything by not executing them, right? So then I can save, but that usually doesn't work out. Let's consider the bomb example. So here, alpha is independent of beta, so I could just execute alpha, and then I could do the same thing, and then I could just miss the bomb, right? So if you ask the property, if you want to check the property, does the bomb ever go? So you might say yes, when actually it does go. So it turns out that the problem really is okay. So the problem really is here, is that at that point, what actually happened was alpha was independent of beta, right? But what you could do was that you have decided to postpone beta. But what you have lost is that by executing beta a few times, you can get to some place that is dependent on alpha. So it's not just sufficient to have everything in your state independent of alpha, but everything you can reach by executing the things you have missed should still be independent of you. So that's the idea behind take two, which is called persistent sets. So in persistent sets, what you want to do is you want to make sure that delta is not just independent of gamma minus delta, but it's independent of anywhere you can reach by executing these sets. Right? Any length in the future. Right? And so in the bomb example, that'll sort of work out. Because if you go here, then now alpha is not a persistent set. Right? Because now I can execute beta for 3 steps, and I can get to something that is dependent on alpha. And so if you use persistent sets, then you do find the error. So it turns out that actually that is also not right. So what you need to do also is that if you have a set of, if you're doing exploration, right, and if you execute delta, and if you don't get any new states, then you have to execute all the transitions. So you have to prove a formal theorem that if you choose this, then what you get is a valid partial order reduction, and the proof is actually pretty complicated. So, but I tried to give you just some intuition using examples. But the high level executive summary is that you use independence, then you have to worry about persistence, then you have to worry about this thing called ampleness as well. So the one thing that happens is that, I'm just nearing completion, is the computing independence relations and persistence set itself is a pretty hard thing to do, because they require knowledge of the state space as well. But what you could do is you could come up with syntactic sufficient conditions. What you could do is you could come up with persistent sets that are larger than necessary because they're easier to compute. And then you could come up with independence relations that are stronger than necessary because, again, they are hard to compute. And still that works out okay. And they offer pretty good reductions in asynchronous protocols, where there's things going on that don't actually relate to each other. And there are few actions that actually sort of communicate. And you have to worry about only those actions pretty seriously. And you could write artificial examples in which they offer like exponential reductions. You could see papers in it say, if I don't use partial order reduction, I blow. And then otherwise I do it in 2 minutes. But in the things that I have experimented with and in the things that I see in papers, if you take systems, it's about 5 to 10 times faster if you have a lot of asynchrony. They're implemented in spin, and they're also implemented in this thing called very soft, and we'll visit this later. So I'll stop here today. Right, thank you.